If you don't think about standing waves, this could be you. When G.I. Taylor was doing his fundamental fluid dynamics experiments, liquid fuel rocket technology was far from well understood. His initial wave experiments were actually more concerned with ocean waves interacting with a breakwater. The foundations laid by his work in such simple standing waves, however, would go on to inform the understanding of complex behaviors such as standing shock waves and hypersonic flow, three-dimensional sloshing, and other phenomena at the edge of current physical understanding.
G.I. Taylor's experimental apparatus was quite simple. It included a tank, approximately 20 centimeters high and 20 centimeters wide, with a system of articulating flaps installed in it. These flaps had springs to create a return force and a driven pulley system to actuate them. The amplitude and frequency of their motion was controlled by varying the size of the driven wheel and its speed of rotation, respectively. In his paper, An Experimental Study of Standing Waves, G.I. Taylor's intent was to experimentally test the analytical results by Penny and Price, and such, it was important that his experimental setup closely resembled their model. Our apparatus fairly closely matches that of G.I. Taylor's, save for a few details. It consists of a fish tank with 2 aluminum paddles controlled by a servo via a pulley system. We used a standard 10-gallon tank and used rubber bands instead of springs to keep the strings taut and the paddles moving. We programmed the microcontroller to step up or down the frequency, holding at 15 cycles per frequency step. We ran the experiment either ascending or descending the frequencies to compare the results.
In Taylor's original experiment, he compared his results to a theoretical solution published by Penny and Price for waves hitting a breakwater. They made a few assumptions about the system, allowing them to derive an analytical solution. First, the system is modeled in 2 dimensions because stable solutions will have a constant cross-section along the width of the tank. Second, water is very incompressible at everyday pressures, and thus constant density is a safe assumption to make for this experiment. Third, at the scale of this experiment, the Reynolds number is high enough that momentum will dominate the fluid interactions, and viscous forces can be safely neglected. The last assumption, irrotationality, states that the fluid has no vorticity. In conjunction with the other 3 assumptions, this allows us to model the fluid using Laplace's equation. Laplace's equation defines a potential function phi, whose gradient is the velocity of the fluid. By conservation of mass, the divergence of the velocity must be 0, giving us a tractable partial differential equation to solve. We can then apply the boundary conditions of the tank. So in the horizontal dimension, the x component of the velocity must be 0 at the breakwater, which in our system would represent a wall of the tank. And by the same token, the vertical velocity component must be 0 at the base of the tank. To model the wave profile, we can define a function f which equals 0 at the surface of the water. And if we examine the behavior of a fluid particle on the surface, its velocity normal to the surface must equal the normal velocity of the surface itself, which gives us a governing equation for the surface in terms of f. Because of the earlier inviscid assumption, we can also apply Bernoulli's equation to find the pressure. And at the surface of the fluid, the pressure must equal the atmospheric pressure, P0, thus setting the whole equation to 0. However, this is exactly how we defined the function f earlier, a function equal to 0 at the surface of the fluid. And so we can define f as the pressure of the fluid according to Bernoulli's equation. We can now plug the pressure into our governing equation for the surface in place of f, giving us a new equation that we can solve. While the actual derivations are beyond the scope of this video, Penny and Price found a solution for both the potential function and the height of the water across the tank. By converting to dimensionless form and solving for the first 5 terms, they yielded 2 final equations for the height over tank length ratio and the frequency of the wave, both in terms of an arbitrary parameter a. And by sweeping several different values of a into these 2 equations, we were able to create a theoretical curve to plot against our actual data.
This is G.I. Taylor's plot of the frequency response. The theoretical curve is represented by the crosses starting at a normalized frequency of 1 and amplitude 0, and increasing in amplitude with a small decrease in the frequency. His measured data points are plotted on this graph as well, as the black dots and their respective lines of best fit. An important thing to note is that there are two data runs presented here. One where the frequency is increasing from 0.85 to 1.15 times the natural frequency, and the other where the frequency is decreasing from 1.15 to 0.85. We implemented this theoretical curve in MATLAB, shown as the blue line on the right. Because we made everything dimensionless, this is the exact same plot as in the paper. Here is our data overlaid with that theoretical curve. We can see that our data has the correct behavior, and that the descending frequencies, shown in the darker orange, drive the amplitude higher than the ascending frequencies, shown in the lighter orange. It also matches the sharp jumps in amplitude due to a small change in frequency, with the descending curve jumping down at a lower frequency than the ascending curve jumps up. This is shown in G.I. Taylor's data as the dashed lines with the arrows on them, where the descending one jumps down at around 0.95 times that of the natural frequency, and the ascending curve jumps up at around 0.975. One thing is that our data seems shifted, and that the frequencies all seem a little bit higher than they should be. And we think this is due to error in actually achieving our fundamental frequency in the setup. If we shift all of the frequencies in our data by about 5%, shown here, our data matches the plot very well. We think that this error is likely due to anything in our system that was actually changing the frequency that was driving the system. So it could be that the servo wasn't acting as quickly as we thought, or something in our setup was slowing things down.
In this video, we showed the frequency response of our system in a descending set of frequencies. The frequencies are displayed on the computer screen on the right side, where 1 represents the sort of natural frequency because these are all normalized frequencies. In this video, we start just above the natural frequency at 1.01. Now we see at 1.01, the amplitude of our system is fairly high. But as you'll see in just a second, it's not quite as high as when we transition to the natural frequency of the system. Now in here we get our largest amplitude waves. But after a little bit of time, we see that the wave breaks into a sort of 3D unstable mode. This is seen in the wave oscillating back and forth into and out of the page. Now we're slightly below the natural frequency, and we can see that the amplitude of the wave has really shrunk quite a bit. As we reduce the frequency even more, we see the amplitude die out even more. Now in this case we still have a little bit of that 3D instability, but as we transition to a lower frequency, we see that it starts to regain that sort of stable 2D shape, but has lost almost all of the amplitude that it had when it was at the natural frequency.
Another thing that G.I. Taylor was investigating was a transition from two-dimensional stability to three-dimensional instability in standing waves. In the paper by Penny and Price, standing waves of finite amplitude were analyzed, and they concluded that the peaks of these standing waves could form a sharp 90-degree crest. At that point, they would become unstable due to the downward acceleration near the crest necessary to maintain their shape exceeding that of gravity. This instability caused the wave formation to break from a two-dimensional pattern into a three-dimensional one, and consequently lose most of the wave's amplitude. This can be seen on our apparatus and agrees well with Taylor's experiment.
So, how can we explain the abrupt transition we saw between large and small amplitude waves? Taylor argued that for frequencies in the transition region, there are actually two possible standing wave modes at each frequency, and the sharp transition in amplitude occurs when the waves switch between the two modes. Here we see 4 still images of waves, 2 each from the descending and ascending frequency trials. Note that the descending frequency waves on the left are reversed from the ascending ones on the right. When the paddles are pushed out, the descending wave has a peak, while the ascending wave has a trough. Let us now observe the transition in the ascending frequency trial. In this initial frame, the wave is in the low frequency mode. The paddles are pushed out and the wave has a trough. As we ramp up the frequency, the wave grows larger and develops instability, becoming slightly three-dimensional in character. If we analyze this last frame, we see that the wave has switched to the high frequency mode. The paddles are pushed out, but the wave now has a peak. Comparing the first and last frame side by side, we can clearly see that the wave has been phase shifted by half a cycle. The paddles are in the same position, but the wave is in the opposite state. This abrupt change in phase is the cause of the instability that we see.